In this video, we're going to look at the Fourier series expansion of a real signal, and we're going to look at a very short signal this time to be able to clearly see the dimensions that we're working with and the number of values we're dealing with at each stage. And what we're going to do especially is look for patterns in the complex output when we take the Fourier transform. And following historical norms, we're going to call that output in the frequency domain Fhat, or if we have the option of writing things nicely, F a little hat over top of it. We'll start with our simple intro of all the libraries, and then we're going to do this line here, which is going to create a random seed number. So basically, we have a random number generator. If we want to reproduce our results, we set a seed so that we always get the same results in this program. And then what we're going to do is generate a set of normally distributed, this is a Gaussian distributed vector of size 16. And we can run that again. Actually, let's print F and see what we see. So we see a number of values. There's going to be 16 of them, 6 per row, plus 4. Yeah, that's 16 numbers. And they're centered around 1, going a little bit higher than 2, a little bit lower than 0, though, in a range there. Really, if we're going to do this, we should be plotting these things. So if we plotted this data, this would be a sequence that looks like the plot you see before you here. What we have on the x-axis, unless we have more information, is simply the index of the vector. So our f has 0 to 15 as the indices. That's 16 total numbers. And we would usually think of this as a line graph. If we had more data, we would usually imagine that these are all connected. But in fact, we don't have the connections. We simply have the data values that we lay out here. All right. So not a lot of pattern to this. That's fine. But we have 16 real numbers. That's the thing I want you to focus on right now. And this is imagine a sound wave over time. Well, what we've done before is we've run the FFT on that. So we said, find me the Fourier series coefficients for this time series here for F. And that's going to be something we get back that's called Fhat. And we saw in earlier cases, and we see it again here. Those are associated with frequency indices, and if we had sample rate and so on, we could turn those into frequencies like hertz, but for now it's just simply the 0th, the 1st, the 2nd, and so on to the 15th. Now, there's a couple things to mention right out of the gate. First off, we started with 16 real numbers, and then we got 16 complex numbers. If we look at our Fhat, we get 16 values, but they're complex. And that means there's really 2 degrees of freedom each one. So actually we have 32 numbers now, when before we had 16. And that should raise some suspicions that something fishy happened there. More importantly for us, though, is the graphical perspective, which also points to something fishy happening. In fact, it looks like this little train of values going down here is matched by these ones going up. And actually, in fact, it looks like it's symmetric through 8. If I just add a little line here, if we can pretend that's a mirror, we would actually see on both sides that the graph is identical except for the 0 point, but everything else is completely mirrored. Well, let's see if that's actually the case. And you know what we're going to do instead, actually? That's a bit of foreshadowing for the next step that we're going to do on paper. What I'm going to do is take these values here and move them over to this side of the axis. So 0, I'm going to make the center equal 0 for a second. And I'm going to take everything from 9, 10, 11 on, and I'm going to move it to the other side of 0 and see what that gets us. How do we do that? Well, imagine this graph that we have now. We had labels for our x-axis of 0 to 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And we're going to stop after 8 and then start renumbering them as minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, and then we'll get to 0. And you can see how we can achieve that through this careful use of the NumPy A range, which lets you use negative numbers as starting points. The regular range function in Python doesn't. So we're going to do 0. Remember, it's up to the last one but 1, so 0 to 8. And this is minus 7 to, not 0, but negative 1. And that gives us 16 numbers that look like this. Now, what's the point of that? Again, think about this plot here, but taking these last 7 values and copying them over to the left-hand side of the axis. And there we can see the symmetry just in a different light. I'm going to add that vertical line again. AX V line, so it's a vertical line at a certain X coordinate. And now we can add X equals 0. Can I do that in red? No, I have to say it's red. There we go. Now we can see the symmetry that we're looking for here. This desperately needs to be explained. We have to go to some paper and say, well, why is it that when I did that, why can't I move these ones down here? And when I move them down there so they're negative, they are the same as they were when they're positive. And actually, are they the same? Well, let's take another careful look at this. If we look at our F hats, we see, remember, we're only plotting the magnitudes. We're plotting F absolute or F hat absolute values, but maybe it's not just the magnitude, or maybe it's just the magnitude that's the same. There's something else going on. Well, it's not just the magnitude. If we look carefully at, say, the second number, let's take the second number here. That corresponds to number 1 here, index 1. And if I go to this, to the last one here, oh, hey, that's the same as this, except instead of plus 0.05 blah, 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 it's minus 0.054 blah, blah, blah. So there's a relationship between these two values, which are now adjacent across the mirror here, in that they're the same complex number, except one has the flip sign of the imaginary part of it. So that's what we really want to explain. And just to make that more clear, I'm just going to load this into a data frame, and just easier to see the numbers. Now, it's still a bit awkward, but we can compare number 1 to number 15 and see, yep, those are the same except the sign change. Number 2 and number 14. Oh, but we made these new indices. So let's practice our pandas skills here a little bit and say for F hat 2, I would actually like to go 0 to 8 and then minus 7, minus 6, minus 5. And to do that, we just set the index equal to what we used here before, which we called K. So that's an alternative indexing scheme. And if we try that, no, that almost worked. We have the negative values there, but we don't actually have it in sorted order, fortunately. You've seen a lot of these sort commands as well. We can sort by the index, and the challenge is if we just run that by itself, nothing happens. We have to use this convention that is helpful when you have huge data sets, which is that transformation we want to do to our F hat, where it is right now. So I want to take this whole matrix, keep it the same name, but just do that sorting for it. And then we get this result that we're looking for. Now, if you look, sort of symmetrically moving away from the center. So this is our 0 in the middle, corresponding to the vertical line. And then we can see the negative 1 plus 1, negative 2 plus 2, negative 3 plus 3s, and how those match symmetrically with the corresponding positive ones. So what this has shown us is that when we start with a sequence of 16 real numbers up here, when we transform that through the Fourier transform, we get 16 complex numbers, which is really code for 32 pieces of information. But what we're seeing now is some of those 32 numbers are redundant. This number, if I had it, I could immediately predict what this matching one on the far side was. And if we take a look through all these numbers, it turns out there's exactly 16 non-zero values here, and these other ones are essentially predictable or copies or simple transforms of the ones on the positive side. So next up, we're going to explore on paper why there's this relationship and what it tells us about how we can interpret the output of a Fourier transform when the input is a sequence of all real numbers, like most of the data that we're going to see.